find out an axis or a direction um, in the input space, so that if you take the projection of this point, if you take the projections, now this projected set of points should be maximally separated between themselves so that they are distinguishable. So that was the objective, that you have to find out that distance, that direction where this maximum separability takes place. I have to remove this diagram. Okay. So for that, what we have considered, that we are trying to pose this problem as an optimization problem, and that also we discussed. Uh, what could be the measure of this separability, of this separation of these two of these two set of projected points? So one measure could be that, as you know, that if you consider the mean of the projected points for each class, then the distance between the mean, that gives you a measure of separation. But naturally, that is not sufficient, because only mean, it's a point observation, and you have a distribution. So you need to also see what is the spread of the projected points. So that is that can be measured by variances, but no, we are considering the sum total of the spread, sum total of the. So instead of variance, we are just simply taking sum of square of deviations from the mean. So that is called scatter. Scatter of a particular projected set of points given a class. So we have two classes, so we have two such scatters. And this definition of the scatter, that you can see that in the for the projected points, it is very simple. It is simply the sum of square of deviations from the mean of the projected points. So it is almost like a variance, but no, variance is the average of this sum, whereas in this case, the scatter is represented as simple sum. So it is highly related with the measure of variance. And if I consider the scatter for both the classes, then I can define the measure of separation. I can define an objective function where this is the definition of my objective function, that since I am considering all square of distances, so I am also squaring the distance between mean, and then it is normalized by the sum of the scatter of two classes. Now, scatter itself, by definition, it takes square of distances, and it's in its representation we use this. This is a kind of represent, like the variance is sigma square. Sigma is standard deviation. So scatter is as a notation we use the square already inbuilt in its term. So if I say square root of scatter, it is a kind of measure of distance. That's what we need to understand. Anyways, that is not very important. Unit directional value, yeah, unit direction, unit vector, in whatever way you you define it. It's a basically unit vector. So that should maximize this particular measure, which is expressed as a function of u, function of this direction j. We call this measure as capital J, and the definition is shown here, which is a ratio between d square and sum of scatter of those classes. So as you understand, that scatter of projected sample should be small. So that's why you are maximizing it. So your denominator should be minimized and numerator should be maximized for the measure of separation. Now that is the concept of scatter for a particular set of projected points. Now we come to the definition of scatter matrix, where we consider the original input space and what is the scatter of data points in that input space. So once again, that is equivalent to the definitions of covariance matrix. The analogy is with respect to covariance matrix. And here also what you can consider that if I consider a the corresponding multidimensional input representation. So naturally, you have to define this kind of scatters in terms of covariances. That means internal the interrelationship between the corresponding dimensions have to be considered. Now, here it is shown, it's a matrix representation, as you can see, that in fact this is what is almost similar to covariance definition. So just to highlight some of the aspects, can you tell me what is this small x? What is the small x here, and what is m subscript capital C? Have you understood? I have already mentioned what is capital C, that is a class. So in this case, what is small x and what is this m subscript capital C?
Input vector and its mean.
Right. X is the data point which is represented like an input vector, and the mean of that input vector, set of input vectors belonging to that class, that is MC. So what should be the dimension of this particular computation? Like what should be the dimension of x minus MC?
D cross 1.
Yeah. So this is a column vector. So the dimension of this would be D cross 1, right? Fine. So what should be the dimension of SC?
D cross D.
D cross T. So how it is different from the covariance matrix of the set of data points? How it is different? So what I should write here in the equation, that would convert it into a covariance matrix. This scatter would be converted into a covariance matrix of that data points, that set of data points.
Total number of, you have to divide by the total number of samples.
That's right. So I have to divide by the total number of samples, this set. So let us consider, say, it is NC, right? NC is the total number of samples, and I have to divide it, and that would give me the actually covariance matrix. Then I would call, instead of scatter matrix, I will call it covariance matrix. When it is, then I will call it covariance matrix. Is this point clear? So you can see there is a very strong analogy between the scatter and variance in the projected space with the corresponding scatter matrix and covariance matrix in the original input dimension. I have discussed also the interpretation of covariance matrix with respect to projections in the last class, and we will see that that kind of relationships are also used here to nicely formulate this particular, to get a solution of this problem and to express the objective functions in a more compact form. We'll come to that. So so let us start from this point that no, this is the definition of a scatter matrix. So how many scatter matrices we will have? Now you have two classes, so you will have independently two different scatter matrices, and let me denote them that by S1 and S2, and sum of scatter matrices is denoted as, say, SW. We call that scatter matrix, that is sum of these two scatter matrices, we call it as within the class scatter matrix. That's the technical term that we'll be using. Okay, is it clear here? You can see that we are not using any notations like square. Earlier we used for the single dimensional or the scalar value the projected on the projected set of points. We have simply we have used these notations of S1 and S2 because they are all matrices. So these are matrices, and as I mentioned, that is the definition of the scatter of the projected points for the class 1. Is this definition clear? Similarly, now this is the interesting part. So you can express the S1 square in terms of, you can see the scatter matrix of that class S1. So you can replace this equation equivalently in this form. Is this clear? Is this no equation is clear to you? Like y minus my1 whole square, that term equivalently uh, replaced by, so this one we are replacing it by this one. Okay, any doubt? So y is nothing but it is a projection of x on u. That is the projected point. Fine. And mean is also projection of its mean in the input space. That we have discussed these two particular properties which can be very easily proved. So projection of the mean is nothing but uh, the mean of the projected set of points, right? And we are simply writing it in this way. Instead of, so these are scalar values, but for our convenience, as if no, we are considering it is 1 cross 1. So we can use simply the transpose operations. So this particular product, the square, can be represented with the uniform notations like this. Why we are doing it, we'll see that it helps us in writing, in expanding this term with respect to the matrix operations. So I hope now this is clear to you. So I can write this in this form now. Now you can see that the same expression is nicely written in the matrix multiplications with respect to the, so I can separate out the corresponding input input data points and its mean of the input itself using this. Is it clear? See, it is a linear operation. You take U transpose outside, it is U transpose into x minus m1. So this one is expanded and this one is expanded. Are you sure? Any doubt? Okay. So now you can see that no, the corresponding summation you are taking over x. So you can bring U transpose and U out of this. That means you can perform the computations using x only, and this U transpose you can bring outside, and also this U you can bring outside. So that means you can put them into the in the middle. So then what it will give you? What is it? So if you take out U transpose from the summation and also U from the summation by keeping the matrix orders similar, order of their corresponding multiplications, by keeping them, preserving that order. So what would be this term, sum of x minus m1 into x minus m1 transpose when you are summing over x? What is this? If you take the sum over x, what it will give you?
Sum of deviations.
What does it mean? Sum of square of deviations, basically. Sum of deviations, right? Sum of deviations, but what does it mean? It will give me a matrix, isn't it? This is the column vectors. So it will give me S1 itself. So this is nothing but it will give me S1. So I can write it S1 square as U transpose S1 U. Is it clear? Any doubt?
Yes, sir. Can you repeat that? What you told? S1U.
Let me write this expression. So is it clear? This is clear to you?
Yes, sir.
Right? So now, what is this term? What is this term? we defined earlier.
Yeah.
What it is called. This is S1. This is a scatter, isn't it? Scattered
Yes,
of
sir. I got. Yes, sir.
class 1.
But
Okay. So we can write it very nicely S1 squared as U transpose S1U. So that is the motivation why you should put into this kind of matrix form, expand it. So you can see that S1 square is written in this way. So what should be S2 square? Because it is the similar, right? Same you can same analysis you can yeah, apply, and that would be U transpose S2U. And if I consider the sum of the scatters projected, the scatters of the projected points, so it is nothing but U transpose SWU, because no, SW is what? That is the within the class scatter matrix, and that is sum of scatter matrices of individual classes. And this is what you get. Any doubt? Okay, so let me proceed. So now let us consider another interesting thing, that is, in fact, so this is the denominator part of that objective function. No, S1 square plus S2 square, that is the sum of scatter, that is equal to U transpose SWU. That is what we found. Now what happens the numerator, which is the square of the distances between means of the projected points, like this square, if you remember this square. Now let us see, actually it has uh, it can be expressed in terms of this particular concept. First, let me explain this concept. We define a term called between the class scatter matrix. So this is a definition, mathematical definition, just simply mathematical definition, but it has certain intuitive implications also. What it is trying to do, it considers the deviations of the mean, that is the difference vector, and it is finding out the corresponding it is nothing but as you can see, uh, yeah, it is deviation of the mean vector of the corresponding classes, and it is considering the corresponding the mm, something like uh, the product of deviations of individual dimensions. That means it captures also inter relationships between dimensions in terms of the products. So for some the deviation would be positive, another would be negative. So it is just capturing those terms like covariances, but only with a single data point observation. So if I consider we are trying to measure covariance with a single point observation among the covariances among the dimensions, among the values in among the dimensions, it is simply doing that. So what should be the dimension of SB? This matrix.
D cross 1.
We're saying D cross 1.
Yes, sir.
Okay, let us see. What is dimension of M1 minus M2? What is dimension of M1 if I say? What is dimension of M1? What is
What?
M1? M1 is the mean of the data point for class 1.
Yes.
So what should be its dimension?
That will be D cross 1.
That is D cross 1, right. So what should be the dimension of M1 minus M2?
That will be some D cross 1.
What should be the dimension of M1 minus M2 transpose?
1 cross D.
What should be the dimension of SB?
D cross D.
Right. You should always look carefully the dimensions of individual components. Then you'd be able to So now you see that no, you had some misconception. You thought that it is a vector, but it is actually a matrix. It's a column vector. You thought it's a matrix. So
Yeah.
that's why I told that it has analogy with respect to covariance matrix of a single data point. If I consider a single data point, and if I consider x transpose, if you do that thing, x transpose, a single data point, that is also covariance with respect to that data point. Do you understand? Right? The same thing what you are doing, but we are considering this vector observation is the deviation vector between two means, right? M1 minus M2. And so now let us try to see that no, what is the relationships between this uh, d square with respect to this? How do you express it? So definition of d square is clear to all of you. My1 minus my2 whole square, right? Is it okay?
Yes, sir.
So now you can express once again the way we have expanded earlier the scatter. Scatter was also, as you see, single data points. It was always a square for a single data observations, and d square is just a single data observation itself. So the if we expand them, it can be written in this form, isn't it? It's the same. Only all x's in that data point are replaced by M1 and M2. Any difficulty? Any difficulty in understanding this expansion?
No, sir.
So U transpose M1 is My1. You have understood, and U transpose M2 is My2. And that is how you are expanding it. Okay. Now, again, the same similar trick. We can separate out U transpose and U, and we can express the in between matrices, matrix multiplications in this form, M1 minus M2 into M1 minus M2 transpose, and which is nothing but U transpose SBU. You can see almost similar form. One was within the class scatter matrix, that is the sum of scatters. Another was one is using the between the class scatter matrix for this, square of distances of the means. So if I write the optimization function, like this was your optimization function, and now I can write it in a nice compact form, which looks very similar to each other. U transpose SVU in the numerator, U transpose SWU in the denominator. I hope the definitions of between the class scatter matrix and within the class scatter matrix is very clear to all of you. Okay.
Yes, sir.
So now the problem, the objective here that we would like to maximize with respect to U. So I will just give you the solution. I'm not going to discuss the steps of mathematical steps, how to derive it, but we can show that the solution would be obtained if you solve this equation, which is a general form of eigenvalue eigenvector equation. So you have SW inverse SBU. Of course, SW inverse, SW should be invertible. That is the restriction, that is the constraint. So in your data point, if you find SW is not invertible, so you should have sufficient data points, right? The rank should be at least the rank of, what is the rank of SW that has to be there if it is invertible? What should be the rank of SW?
Full rank.
Yeah, full rank. That it should be invertible. What is the dimension of SW? Full rank means what? I want the answer.
D.
D, yes. That means the dimension of the space. So minimum, how many observations you should have? You should have D observations, I hope. Huh? Minimum D data points you should have. You just check it. So So that is the kind of, there are certain restrictions over that. I made an off the mark comments, but you can check it. So these are interesting observations. So now the solution of U, it comes in a very interesting way. I will give you another intuitive observation. The observation is that now for the between the class scatter matrix, if I multiply any vector Z, that's the column vector, that's of the same space. If I post multiply with any column vector Z, it would be always in this form. That is some scalar value k into the vector m1 minus m2, because of the structure of SB. So which means if I multiply SBU, it has to be a vector proportional in the direction. I mean, it has to be in the direction of m1 minus m2. So why it is so? Let us understand. If I expand SB, you get what? M1 minus M2, M1 minus M2 transpose. That is what SB. Agree? Definition of SB is M1 minus M2 into M1 minus M2 transpose. And then you are multiplying with Z. So why do we say that M1 minus M2 transpose Z will be like a scalar vector? Sorry, a scalar value? Why do we say that this computation will equivalently give you a column vector m1 minus m2 multiplied by some scale factor? That means the directions will always be in the direction of m1 minus m2.
Because M1 minus M2 transpose into Z will be a 1+1 element.
Yeah, I mean, that is one way. It's basically dot product of two vectors. And it has to be always a scalar amount. You are right. Okay. So this is very interesting because I can now replace this equation as SW inverse K into M1 minus M2 equal to. So since this is this eigenvalue problem, eigenvector problem. So U can be written as SW inverse M1 minus M2. That is what U should be written. And you will be taking the unit direction. Finally, no, you have to take the unit vector direction. What you want is the direction. So that is your solution. So only direction matters. That's all. Right? So is it clear now how your Fisher's linear discriminant could be obtained given this kind of data points of two classes? So all our discussion is with respect to two classes. So I'm not going to discuss the multi-class problem. There is an extension of this particular theory even for multi-class problem, multi-dimensional projection. So I'm only projecting on a particular single directions, and also I'm considering two classes. So but no, it is very interesting. You see that here the direction of the vector is m1 minus m2 into SW inverse. It is not, the direction is not along m1 minus m2. That you should understand. Direction could be different then, because SW inverse is not a scalar value. SW inverse is a matrix. So it's a transformation. It's a transformation matrix. So you are just transforming that direction. You are transforming that direction. So if your scatter happens to be something like identity matrix, if you're within the class scatter happens to be identity matrix, then it is the same direction. That is what it is saying. So let us again illustrate using an example, which is once again a toy example with very less amount of data points. So we are considering once again three-dimensional space, and you can see now the specification. It has two sets of input data points, each for one class. So you have, it's a, I should say that's why this technique is called supervised technique for finding out for this kind of discriminant analysis. PCA was an unsupervised, where this class information is not used and is not required as per the theory. So we have to do, I will be doing two things. One, I will compute the LDA or linear discriminant using this particular analysis given the class information. And I will also compute the direction of the principal component, the first principal component, ignoring the class information. And then I would like to see that, what is the effect on the projected set of points, whether that separability of the classes in the projected space is maintained, how it is maintained, how it is, because we say that it should be optimum for LDA. So it should be better for PC. So the computation proceeds in the same way. I hope you have understood this representation. There will be two input data matrix for each class. Is it clear? So which are the data points here in X1, rows or columns? Which are the data points for X1?
Data points will be column vectors, no, sir?
Yeah, they are all columns. Huh? So you have data points like 532, 460, 3 minus 714 like this. Don't read 543, etc. But because in our context, we have considered always all these analysis, all these expressions, we have assumed our representation of data as a column vector. And so mean of class 1, that is M1 in our discussions. Huh? And this is the mean of class 2. So what is the solution then? Solution is, first you have to compute also the difference between these two means, M1 minus M2. And then you have to compute the within the class scatter, right?
Yeah.
So S1 is the within the class scattered. If you compute S1, that means the definition is that you subtract mean from each column of X1, and then you multiply X1 with X transpose. I mean, if I say it as X1 tilde, then multiply with the transpose of it, that is the scatter S1, because we are not doing any averaging to get a covariance value. We are happy with the scatter matrix S1. Similarly, you do it for the class 2, and you get S2 using min 2 and X2. Any confusion at any step, please tell me. So these are the definitions. So SW, that within class scatter, is S1 plus S2, and this is given this. So now you tell me what should be the solution. What is the expression of the solution? What I need to do to get the direction of maximum separability for the projected space. What is the solution? It is SW inverse into min 1 minus min 2, right? This is the solution. And you will get a vector like this. Now you have to normalize it to make a unit direction. So if I consider the separability, you may normalize here. I have not normalized it. Actually, these will be all scaled up, so it doesn't matter. So you can see that these are the projected values. So the range of y1, it lies between 19.31 to 22.2 for this set of data points, and here it is 5.43 to 9.55. By observing this, now we can make a decision. Suppose I will say that if the values are all say let me put a margin of say 15, just no, it is heuristic. It is a kind of heuristic guess, intuitive guess. So if I put 15, so all the projected values, if it is less than 15, I will say those belong to class, no, those belong to class 2, and greater than 15 would be class 1. So that kind of simple rule you can define. So you can see that linear discriminant and Fisher's linear discriminant analysis directly does not give you the rule for classification. So rule for classification, once again, you have to derive by observing the set of projected points, by observing their span, by observing their separability, etc. There may be overlapping. You cannot guarantee. It is trying to get a directions where no, you are most likely get the maximum separability. That doesn't mean they may not be. So in this case, toy example, no, it has been it is found to be non-overlapping, but it may not. And in these are all training data. In test data, they may not be. So there would be always no classification error, etc. All those things will be there. Even the training error would be there. But no, this is what maximally you can do. Maximal performance you can get if you apply this analysis with that constraints that no, it has constraint of our problem definition. So well separated in this case. So now let us compute the principal component. So now in this case, you have all the data points into a single data matrix. You see that all the columns, they make the data points. And since there were 6 data points, so you have a dimension of D is 3 cross 6. Each column gives you a data point. Okay, so you should tell me that what are you going to do for finding out the principal component. So what should be the first step?
Finding the mean.
Okay. Then
you have to find the difference. X means the covariance matrix.
You have to find the covariance matrix. Right. So I'm just simply writing covariance. I hope you'll be able to find out the covariance matrix doing that. That means what you are trying to say that take the difference for individual columns from mean, and then you multiply X with the transpose of the transformed matrix, multiply the matrix with its transpose, and then of course you have to divide it by the number of samples. Then it gives covariance. Otherwise, that becomes scatter of data points as per our discussion. So we did all those things, and we get this covariance matrix, and then you perform the corresponding
eigen calculations.
Eigenvalues and eigenvectors. So eigenvectors will give you the principal direction. So first eigenvector, that means whose eigenvalue is 72.96, and you can see that how much of variance it is accounting for of the total variance. So principal components, let me enumerate all of them, and only the thing which we are considering here, that is colored by this kind of color, maroon color kind of whatever color you call it. It's not red. So that is the first direction of the first principal component, and we have taken the unit vector in this case. And then what we are trying to do, we are trying to take projections along these first principal components. So we are trying to study the separability. Now we will be considering 2 sets, and now we use the class information. While studying separability, use the class information. So you set of points belonging to class 1, and from this set Z1, and so these are the set of projected points. So I'm just representing from that data matrix X1. If you do it, it will get. So this is the set of projected points, and this is the another set of projected points. So now you can see here. Is it overlapping? Do you think it is overlapping? It is not overlapping, isn't it?
No, sir, it's not overlapping.
Yeah, but still, you see that the margin of separation is much reduced, very small. So it is not ensured that no, it is the best direction. That it just shows. Okay. Is it clear? I said it is overlapping. I think no, I made a mistake. So it should not be overlapping. No, yeah, no, it is not overlapping. Right, sorry. So it is not overlapping. I will correct it. Okay, so let me come to the conclusion of this particular topic of dimension reduction. And we have discussed about three different things under this topic. One is that selection of features, because dimension reductions, two major approaches. One approach is that you can select a subset of features given the features and use it for the representation of the corresponding object. That is your that is the representation. So appropriate feature which are relevant for the purpose of the discrimination characterization. The other techniques where you are trying to represent you are trying to remove the redundancy in representations, and that is the unsupervised way, and use less dimensions. So I should say rather you are trying to obtain the minimal subspace which is sufficient to represent the data points. That is what one approach, unsupervised dimension reduction method we have considered. Dimension reduction method, the last one which we discussed with respect to class information. So forward and backward sequential selection methods in feature selection. The second one we consider principal component analysis, and the third one is linear discriminant analysis.